Hi everyone, been working on a little project here with my old ZX Spectrum. I wasn't intending on doing a video for this one, I was actually intending on doing a proper project web page for my website. However, I've come across a little problem with my ZX Spectrum project, so I thought I'd document it. So basically, back in the day, I used to play about with these ZX Spectrums, playing games, writing software, mucking about with the hardware, that sort of thing. So I've dug it out from a box in the loft and just sort of have a look and see if I could get it working again, which I have managed to do. However, things have moved on a little bit from there. I couldn't say no to mucking about with the hardware again, so I've actually started to develop an interface that will plug into the back of the unit. One thing that these old ZX Spectrums didn't have, and that was sort of like a multi-IO interface, basically analog inputs, analog outputs, digital in, digital out, and possibly even other things as well. So I thought I'd actually develop a new interface to plug into the back, just purely for fun. I'm not planning on selling it or anything like that, but I was going to go as far as creating a proper Rigol PCB file for it and all that sort of thing. So I'd actually started developing an interface, and if I just pan the camera across there, you can actually see my new board there, which is plugged in. So basically, you've got digital input and output, and you've got a couple of an A to D and a D to A IC, all running off an I2C bus. Of course, the ZX Spectrum doesn't have I2C natively, so I've actually had to employ the provision of parallel to I2C converter IC, which then in turn drives the actual A to D and D to A. So for the most part it's up and running. It's all totally coded in BASIC, and I don't really know that much machine code, even on these old Z80s, so I thought, well, I'll dig into the BASIC and I'll get it up and running. So that's what I've managed to do. So we'll take a quick look at the schematic. Sorry for the hand-drawn nature. Basically, this is the ZX Spectrum edge connector here, where you've got basically the data bus, a few address lines, the read and write lines, IORQ lines, that sort of thing there. And basically it comes into this I2C 55, which is a pretty common IC, basically giving all the buffering and the latching necessary in order to provide 3 8-bit ports that are configurable as digital inputs and outputs. So fairly easy to interface this to the ZX Spectrum interface. Up at the top left hand corner here we've got the 74LS138. That's doing a little bit of address decoding along with the 74LS86 up at the top here, and basically it's providing 8 chip selects effectively to the various ICs on the board. So one of them obviously going to the I2C 55, the other one coming away down here off to a PCA 9564, and this is also connected to the Spectrum data bus, and that's basically a parallel to I2C converter IC. So a database interface at the bottom, and as you can see here you've got the SCL and the SDA, that's your I2C interface. Then obviously you've got the various read-write lines and chip selects at the sides there. The other two ICs, that's basically an A to D chip and a D to A. The D to A chip's a DAC 8574. Basically that's a quad channel 16-bit D to A converter IC. Obviously it runs off the I2C interface there. And over on the right here is the MCP 3424. That's the A to D 4-channel again, and that's configurable from 12-bit all the way up to 18-bit through a configuration byte, and that's actually where part of the problem lies. The only other thing I've got on the diagram is the D to A chip's the only chip that needs an external voltage reference, so I've got TL431 hooked up there, which has given me, I think I've got it configured for about 2.5 volts DC VREF. So everything's working, the basics of it are all working, the digital I/O is working, the D to A is working nicely, the A to D is working, although that's part of where I have got a problem, and obviously the parallel to I2C interface is working as well. Okay, I've actually got it up and running now. You might hear a little bit of a clicking in the background. That's actually the ZX Spectrum. I've got it's beeping every now and then as the program's running. One extra thing I do have in here is I'm using a SpectraNet interface plugged into Spectrum, actually between my board and the ZX Spectrum, and what that's doing, it gives the ZX Spectrum an Ethernet interface, TCP/IP, and it's just, I'm actually just using that as a ways to download my new software very quickly and easily easily to the spectrum so that I can make quick changes and compile the code and then run it for my board. So it doesn't get in the way at all of my actual interface. It's quite seamless really. I'm using different ports and all the rest of it, so there's not any clash of ports or anything like that there. So just in case you're wondering what that board's doing. So I've got it up and running now. Basically I'm testing out the D to A at the moment, and as you can see I've got my meter hooked up onto channel 1 of the D to A chip there, and you'll actually see the voltage is rising there. I think I've got it configured now 0 to 4.095 volts, something like that there on the VREF. Basically it's the 16-bit output on the spectrum is counting from 0 to 65535, and then it goes back to 0 again. So that corresponds to 0 to 4.095 volts. There it is, it just jumped back down to 0 again, and that's off it goes. And I've got it going up at 10 bits at a time because the spectrum is quite slow, so it would take ages to cover the range 0 to 65535. So I'm going up 10 bits at a time there, so therefore you can see it does actually take a little bit of a jump there. And if I swing across to the actual display on the spectrum, just a little test screen that I've got running, you can actually see there, just get a bit of focus here, you can actually see the 16-bit number there counting up, and that obviously corresponds to the voltage I'm getting out on the meter there. So the D to A is working fine. I haven't bothered coding up channels 2, 3 and 4, but I know that channel 1's working, therefore everything's configured nicely and it's running away. The only other thing you've got at the top of the screen there is actually the digital ports there. I've got a couple of keys in the keyboard I can use to set bits on any one of the 3 ports. So there's the, just happens to be that port A is on display there. There's the 8 bits of it there, and bit 0 is actually set to 1, so that one will have gone high. And I've got basically 8 LEDs on the board which will correspond to that port A, as I've called it there. And you can see the last command that I sent to bit 0 of port A is set to 1, so that was that there. So basically I've not got a problem with that at all. The problem is with the A to D, but we'll get to that in a second. Okay, I've gone ahead and actually enabled the A to D routines there. So I've got on the display here channel 1 input, which I'm monitoring on the screen here. The first digit there, that's the actual raw data basically from the A to D, and this is it broken down into the MSB and the LSB there. So if I've got a pan round here, so I've got a voltage source there hooked up to channel 1 on the actual A to D chip over there, and this is me displaying it on the screen here. So if I just wind up the voltage off screen of that A to D, you can basically see the raw data there going up. By default, unless you send any configuration codes to the A to D chip itself, it defaults to 12-bit operation, which is actually the lowest resolution of all 4 of the inputs there. Okay, so the input range of the actual A to D chip's actually bipolar. It's not 0 to 5 volts or anything like that. It's actually from minus 2.5 volts to positive 2.5 volts. There's no external VREF on the MCP3424, so basically you're normally fixed across a bipolar range. So by default it's minus 2.5 to positive 2.5 volts. Now my little voltage simulator off screen there is only set up obviously for a positive going voltage, so basically I'll only see 1/2 of the range. So the raw data that I should see here should be 0 to 2048. So if we just roll it up here off screen up to, well, let's get it to 1 volt approximately. So there's obviously 1 volt there, so that's 1024 it should be. And if I go all the way up to 2 volts, I think it's actually 2.048 to be totally accurate. So there's around about 2 volts there, so that's your almost at the 2048 there. So obviously if I put in minus 2.048 volts, I'll get the other half of the range there. So I'm only getting 0 to 2048 there. And that's where the problem actually lies. There's a configuration byte that you can send to the actual A to D chip itself via the I2C bus that can change the resolution and a whole bunch of other parameters within the chip itself. Now, I've used this chip before. It's actually the same IC that I use in my home-built bench power supply, so I know how to use it, really. But the problem is with the experience at the moment is, no matter how I try to send a configuration byte, it just doesn't able to be received by the IC. Therefore, I'm stuck in 12-bit mode all the time. Played about with the code, repositioning where I'm which point I'm sending the control byte, and it does some weird and wonderful things to the resolution here. It jumps it sky high and does all sorts of weird and wonderful things, but I can't just simply change the one byte that tells the device to go into maybe 16-bit mode or 14-bit mode. It just doesn't seem to be received in normal operation. So I thought, played about with the code for as long as I can, and I just don't seem to be getting anywhere. So what I've done today, actually, I've actually hooked up my Rigol oscilloscope, which has got an I2C decoder built in. So I thought I'd hook that up and see how, if I can actually monitor the actual I2C itself and see if my actual commands are getting onto the bus. Now, bearing in mind that the parallel to I2C converter chip actually sits between the actual data bus, obviously, and the I2C devices, this is actually, I'm not actually writing directly onto the I2C bus from my code. I'm actually going through this chip. Now, however, this chip, it does need setup itself. It actually lives on 4 ports. That allow you to configure the bus. You might want to change the speed of the bus and a whole load of other parameters, and you do that through the data bus and actually 4 available ports. Basically, one of the ports is a data port, the other one's a configuration port, and there is actually another couple of ports. Now, once it's up and running, the data from that point onwards that I want to actually send to the devices is actually sent on one of those ports. So basically, port 29, as I've got it set up, is the data port, but depending on what mode you're currently running in, you might be sending data to this chip and not necessarily to the devices further downstream. Or obviously, once it is up and running and you've cleared the way and started the converter running in normal operation, that port 29 is actually used to send data through the IC to the actual I2C devices. And it's that problem I think I'm getting at the moment. The Dte chip was fairly easy because you're sending data in one direction only. I'm not really doing any meaningful readback. It's just sending data from the port through to the Dte chip. However, the A to D chip's actually a different story. In normal operation, you will be reading back data from the A to D. However, you will actually have to write to the A to D chip if you want to change things like the resolution, from 12-bit to 14-bit to 16-bit to 18-bit. And that's where I think the problem is, because this chip here, you put it in a write mode for the device you want to send to, or you put it in a read mode. And trawling through the datasheet, it's not exactly explicitly clear that if you put the device on for that particular channel in read mode, i.e. you've connected an A to D chip that you want to take data from, can you actually send data out even though you've put this chip in read mode to the device in order to make configuration changes? Or do you have to go and tell this chip to go into write mode, send your data through, then reset, turn it into read mode, and then pull the data from it? So I played about with all that. I wrote some test code to do exactly that, and it wasn't any better or any different from just running continuously in read mode and then trying to send data to the A to D. Now, bearing in mind that I was getting what appeared to be some resolution changes, possibly for up to 18-bit, depending on where I positioned the commands, the configuration byte command in my software. So playing about with that, looking on the web, don't really see anybody else using this chip. There are Arduino libraries which may give me the information I need. However, Arduino libraries are probably going to be big and written in C++, so trawling through them to try and find what I need is probably a bit too much in depth. So like I said, what I thought I would do is hook up my Rigol oscilloscope, put it in decode mode so that I can actually decode the data directly on the I2C bus. And the plan is I'll disable the D2A chip so that I'm only using the I2C bus for the A to D, and we'll see what is actually coming out of this chip onto the bus. Are my configuration commands getting through? I'll be able to see the data coming read and write basically on the bus. So that's the next thing to do. Okay, so what I've gone ahead and done is I've actually disabled the A to D on the in the software, and I'm actually only monitoring the D2A chip. That'll be the only active device on the I2C bus, because the first thing I wanted to actually do was actually monitor something that's working so that I can make sure that the Rigol's set up rightly so that I'm seeing the correct data on the Rigol itself. So I'm actually got that running now, and actually if you can view there, I've actually got that's 4C hex. I'm zoomed right in on one of the bytes that's been sent out on the I2C bus to the D2A, and that's actually 4C, and I know that is actually one of the bytes that is sent out from the software. But I'm not interested in any particular byte in detail. I want to actually monitor the actual data itself as a whole. So if I just go into the event viewer here, so what I'll actually do is I'll actually change the time base a little bit so that I can see more data on the screen at once. The I2C speed is actually very, very slow. Well, the speed's quite fast actually, 88 kilohertz, but because the spectrum's so slow, it's actually sending out on the I2C bus very infrequently, so you can't actually see a lot of data on at once. But if you look at this green line here, those little ticks there, that is actually data going out, and previously I was zoomed in on one of them. But of course when I'm zoomed right out like this, I can't actually see the data, I can't read it. So the best thing to do is turn on the actual event table there, and I can actually see the data. So I'll just hit stop on the spectrum. So there we go. The one below is a bit incomplete, but the one at the top there, that's a complete command. So you're seeing in decimal here 32.116.255, and that's actually quite correct, because when I'm actually sending data to the D2A, 32, because it's a quad channel D2A IC, basically each channel has an address, and I've got it configured, it's 32, 34, 36 and 38. So obviously because I'm sending to channel 1, 32 is a channel. Then you've got 116 and 255, that's basically the MSB and the LSB bytes corresponding to the 16-bit number I'm sending. So as I said earlier, I've got the SpectraNet, the Ethernet interface card on the Spectrum hooked up to my home network here, as I do have my PC, and this is actually my development PC. So on the left hand side here I've got my source code. It's not ZX Basic, it's a form of ZX Basic that somebody's written that basically extends a lot of new commands into ZX Basic, and it allows you to put in comments and all that sort of thing without silly rem statements and all that sort of thing. So basically I'm running that there, and basically what I do is I compile that to my machine code file, or a tap file as it's called. On my other screen here I've basically got it set up, it's a small Windows executable. It takes the source code, compiles it to a tap file, and then within the same batch file I used to do that, it actually goes and puts the tap file into a particular folder on my hard drive, that when I reboot the ZX Spectrum, the first thing it does is when it boots up, it goes on to my network to a particular folder, picks up the tap file, pulls it across the network, and then loads it into Spectrum and then boots it. So basically it's really fast to roll out any small changes I make to the source code. It's just a case of make the change, save the file, hit F3 in my command line box here, it'll compile it, put it in the folder, and then just reset the Spectrum. That's all I need to do. So go ahead now and disable the Dte routines on the software here, and then we'll get back onto the Rigol. And here it is actually. This is actually the main loop in my software. Nice and small, just doing basically a lot of go subs or go tos, that sort of thing there. So I've got one line here which is the go sub for the A to D, and I've got the other one which is a go sub for the D to A. So like I said, at the moment I'm running with the D to A only. So I want to enable back the A to D, so I'll basically comment out the go sub there, and I'll hit save, hit F3 in the keyboard. Compiled that, just runs my batch file. That's basically compiled and copied, and it's now on the Spectrum now. Okay, so now I'll reset the Spectrum. Got a nice little button here, easy to do that. So there's the Spectrum booting up directly to the Ethernet interface, and basically it's now sitting with a tiny little basic program on it that's basically going to load the tap file that's sitting on my network across the network into Spectrum. So I just hit run there. And that's it, pulled it across the network, and that's the software up and running, dead easy. Well, just before we go any further, just back to source code again so I can show you what's going on here. There is actually a routine that runs at boot which basically initializes the 9564 parallel to I2C converter IC. Basically all it's going to do is turn off timeout function, set the address of the actual converter IC itself, and then set up the I2C clock frequency, 88 kilohertz at the moment. So basically all that's doing there, and like I said, the actual 9564 has 4 ports that it uses for a mixture of configuration and sending data, and it's actually there's port 43, port 13, that sort of thing there. So basically that's done at boot up, and then further down here, this is actually the Dte routine here. It's not very big. Let me see if I can just get that on screen. So it's basically that's it there. That's the routine for basically sending to the D to A. So we'll ignore that at the moment, and we'll go to the A to D routine, which is there. Basically, port 61 is used to start the I2C interface, and then on port 29, which is a data port, it's going to basically load the slave address of the I2C device, obviously the A to D chip, and tell it whether I'm reading or writing to that device. Obviously I'm going to read from an A to D, and basically loads that into the converter IC, and then basically it resets a couple of registers when it's finished doing that, and then from that point onwards I'm into the A to D, pulling the data off of the A to D chip itself. Down at the bottom here, if I just jump down, basically here we go, we're reading from the actual here, that let AD receive I equal in 28, so that's reading a byte. I've got a small array, it's just a 2-byte array at the moment for pulling the data out. It pulls it out 1 byte at a time, most significant and least significant. So basically I'm pulling that into a little array, and obviously I'll go and process that later on, but this is the point here where it's actually pulling the data, and that is working. I'm actually able to get, as you've seen earlier, a nice 12-bit number reading on the screen there. However, that's not what I want. I want a 16-bit number. So further up here, I've got, it's remmed out at the moment, commented out at the moment, but basically I want to set up the configuration of the actual A to D itself, i.e. I want to initiate conversion, I want to read back on channel 1, I want it to be a one-shot or a continuous conversion, I want 16-bit, I want a ×1 gain, all that sort of thing. You build up a byte based on this binary information here, and 136 is basically the information I need for it to be 16 bits, one-shot, channel 1, that sort of thing there. So basically I'm wanting to use port 29 there to send out on. Like I said, I'm reading back on port 29 down here, the actual data, but I want to send out on port 29 the configuration byte. However, that's not being received, or doesn't appear to be received from the actual A to D. And like I said earlier, I'm thinking maybe it's got something to do with the I2C converter IC, that you're having to set it up for read or write only sort of thing, depending on what device you're looking to connect to at the time. And like I said, the datasheet's not really that explicit about whether you can send out to a device when it's in read-only mode. I'm not too sure. So I've commented it out at the moment so that I'm basically only reading from the A to D. First thing I want to do is I want to be able to see on the Rigol there that I'm actually seeing the data coming in from the A to D chip itself. Then what I'll do is I'll enable this configuration byte here, and then we'll see what changes, if any, we get on the Rigol. Okay, so we've got the A to D up and running now. So basically on the Rigol there, you can see that I'm doing a read, so that's perfect. And there's the actual data there. I've got 3 bytes listed, 0, 5 and 16. The voltage source is down basically at 0 at the moment, so more or less that looks like data at the bottom end. So if I just start winding up the voltage there on my voltage simulator, you can see there that looks like that 119, that's the least significant byte. So if I just keep going up, yep, rolls over 255 and basically onto the most significant one there on the first byte there. So I'll just keep going up, and it's just perfect. It's got the most significance increasing, as is the least significant, all the way up to roughly 2 volts. Which should be 7255 there. So that's basically the range in the 12-bit mode. The extra byte at the end that's coming in, 16. So we'll have to have a look in the code there and see what I'm actually doing with that. I think I'm only pulling the first 2 bytes, but the actual A to D is only sending, is actually sending 3 bytes. So I'll have to have a look in the code there. Maybe I should actually change my small array to capture 3 bytes and actually capture that one, because I'm not too sure what it is at the moment. It seems to be permanently at 16. However, first thing I think I'll do is I'll enable the write back, and we'll see if we're actually getting another line on here that's actually writing back to the A to D. Okay, I've enabled the write back, and as you can see, looking at the Rigol there, I'm still only getting reads. I'm not getting any writes. I should be getting that 1 write per loop, i.e. per conversion or read back into the software. So if for every read I get, I should be getting 1 write, and I'm getting absolutely nothing. So looking like it's what I thought it might be, and the actual converter IC's blocking the write backs. So it looks like I'll have to do something in the code so that I'm able to write back. And so what I think I'll have to do is break out that one subroutine into 2, and basically for every loop have it configure the converter IC, the I2C converter IC into write mode, send the configuration byte, then then configure the converter IC into read mode, and then pull back an A to D conversion, and then just routinely go round and round and round that. Okay, that's the software modified now, and as you can see, success, I'm getting alternate read-write, so this is exactly what I was looking for. You can see the readbacks there are as per normal, although I am getting a 4th byte. We'll come to that in a minute. And you can actually see again, I never mentioned this before, but you see the ID there, 69 hex. That's actually the address in hex of the actual A to D chip. That's what I'd set there. So you can see it reading back, and hex 69, the actual data there. If I just wind up the voltage source, you can see the first 2 bytes changing again, although there is this extra 4th one. But as you can see, importantly, I'm actually getting a write back to the A to D chip. Curiously though, it's on channel 40, and that might be why the A to D is never receiving it. Not too sure why it's the content of the data is 3, because that's not what I'm sending out. I'm sending out 136 decimal, which is nothing like 3. On actual, the destination's actually channel 69 as well. However, it seems to be writing out to channel 40 if I'm reading that correctly. Okay, I've made a further change to the software here. Basically what I've done is I've isolated the subroutine. I'll send the write configuration command only to the A to D chip, and it's still getting there channel 40. So I went back to the enabling the D to A IC only, i.e. commented out the A to D chip totally, and I'm getting 4C in there, which is actually correct for the address of the D to A chip. Now, given that sending data to the D to A chip is almost identical to sending data to the A to D chip, I should be getting, if the address is working in one side, it should be working on the other side as well. So there must be some difference between the routines that I've got for sending data to the D to A chip in comparison to the A to D chip that are somehow causing it to change from the address it should be to channel 40. And of course the data it's actually sending looks like it's got corrupted as well. So I need to go and look at the two subroutines in the source code and see what the difference is. And look at that, got it fixed. There we are doing the configuration of the A to D on channel 69, and I'm sending 136, which is the configuration byte for setting up the 16-bit mode and all the rest of it. So what was wrong? Let's take a look at the source code. First of all, quick recap. So here's the subroutine for the D to A, quite short, and below that there's the subroutine for the A to D, which is, like I said, is doing the read back only. So figuring I needed to put the converter chip into write mode first before I can send a configuration byte. I'm not going to do it within the read mode, so what I've done is I created a new subroutine here for sending a configuration byte to the A to D by putting the converter chip into the write mode first. So I've done that, and there's the data I was sending, out 29136. However, that wasn't working. It was somehow or other getting to the Rigol is coming out in channel 40 and not channel 69 as I had set up here. So what was wrong? Well, there's nothing much difference between the routine sending to the A to D compared to the D to A. So I figured there must be something different here. Before this one's working perfectly. So looking through the code here, I've basically got 3 outs here, sending some configuration setup and all the rest of it. Then I was doing a bit of housekeeping here and preparing the data to go out to the D to A, and then I was actually sending to the D to A there. There's out 29. So there was a little bit of extra work being done there in the code. Now going down to the new routine, basically none of that housekeeping was being done, so I was going directly from sending the configuration data to directly sending out 29136. So what I've gone ahead and done is introduced a tiny little pause 5, and that's all I've done. And basically that's simulated that little bit of a time delay before actually sending out the data. Strictly speaking, what I should be doing is sending data out to either of those chips and then getting an acknowledge reply, acknowledging that in the software before doing anything else. However, I haven't bothered employing all that at the moment. One of the reasons is just the time involved in doing that, but number two is the spectrum is quite slow. However, sequential outs like this are going to be, quite fast, so therefore I think I do need the pause there. So I've gone ahead and done that. I've given it quite a lengthy pause just to make sure it's okay. So I think the next step now is, now that I've got that running, I'll go back up to the top here into the main loop, and I'll now re-enable the A to D subroutine itself and also the D to A, and we should be getting hopefully everything working on the Spectrum screen. And there we go, that's everything enabled. So now looking at the Rigol there, and if I just freeze it at some point, there we go, we can see the writes to the D to A on 4C, the read from the A to D on 69, but importantly there's the write to the A to D on 69 also, and the data. So that's all working there. So now let's take a look at the actual Spectrum screen. So there we go. So I've got, let me wind down the simulator. So there's the voltage simulator, right down at more or less 0 volts there, so that's at the bottom end there. So I'll start rolling it up. And as you can see now, I've configured it as a 16-bit numbers, which I was wanting. So if I go up to 1 volt, so that should be 16384. That's great. And then all the way up to 2 volts, should be 32768. Now that's right, bearing in mind it's bipolar, so the other half I'm not seeing, I'm only seeing basically 0 to 32768, so that's perfect. And you can also see on the screen there the corresponding MSB and LSB. So let's screw it up a little bit further, there you go, 0 to 32767 as it should be. So that's it working great. So without the Rigol it would have been a bit hit or miss there in order to troubleshoot this. So it's really the first time I've used the decode function on the Rigol in anger, but it's actually enabled me to get to the bottom of this problem, because I had spent the best part of a good few hours just tampering with the code, playing with it and all the rest of it, but a little bit blind and just trying to see if I could make this basically go from 0 to 32767, which I was unable to do. It's not until the brainwave this morning, wait a minute, I've got a Rigol, I should be using it, I've got the I2C decode function on it, let's get into it. So it's exactly what I've done, and as you can see there, it's done the job for me. So I hadn't anticipated doing a video on troubleshooting of this particular problem. I'm just producing a project page on my website for the whole thing, including CADing this up in Eagle PCB and generating a full-blown Spectrum compatible interface board. But I thought with the problem I've got and the process going through to troubleshooting it, I thought it was quite interesting, so I thought it worthy of a video. So I hope you enjoyed that, and maybe I'll be back with a video camera a little bit further down the line when I've actually got a proper board on here. So thanks for watching.